Hello and welcome to Electromagnetics 1. My name is Chris Trample. This is the second lecture in this course. It's called Coordinate Systems and Transformations. One of the big tasks that we have in this class is to be able to represent the fields in three-dimensional regions. In order to do that effectively and quantitatively, we need coordinate systems. And it'll become apparent as we move along that in order to analyze certain geometries, particular coordinate systems are advantageous. A point or vector can be represented in any curvilinear coordinate system. In other words, in a Cartesian, a circular, cylindrical, a spherical, elliptical, cylindrical, parabolic, cylindrical, conical, prolate, spheroidal, or oblate spheroidal coordinate system. So in other words, there's a number of different coordinate systems, all right, that we can use to represent vectors, which technically are not determined by the particular coordinate system. You can represent the same vector in Cartesian coordinates and in cylindrical coordinates, for instance. Okay, so vectors in some ways are just simply not tied to coordinate systems. An orthogonal coordinate system is one in which the coordinates are mutually perpendicular. Those are the kinds of coordinate systems we're going to be focusing on primarily in this course, the ones in which the coordinates each are mutually perpendicular. Analytical solutions to problems depend on choosing the appropriate coordinate system. This is pretty important. With the advent of modern computers and numerical solutions to problems, we don't always have to solve problems analytically. In other words, using closed form expressions. However, there are things that you can see from those analytical solutions that are very useful. And so we're going to develop the ability to find some of those analytical solutions. Well, the first coordinate system that we will consider here is the Cartesian coordinate system. It's named after René Descartes, who was a 17th century philosopher and mathematician. A point P can be represented using three numbers x, y, and z. The range of x, y, and z is from minus infinity to positive infinity. Okay, so these are the familiar coordinates that you use in high school. In the Cartesian coordinate system, we can represent a vector using, again, these three numbers. Each of these numbers, a sub x, a sub y, and a sub z, are the components of the vector, we would say. So we can write a vector A that's pointing in some direction there in three-dimensional space in this way, or we can write it in terms of its coordinate times a little unit vector. So a sub x times x hat plus a sub y times y hat plus a sub z times z hat. If you look at this figure over here, they're showing you the three coordinate axes. And if you'll notice, the Cartesian coordinate system is orthogonal. The x-axis is at 90 degrees to both the y-axis and the z-axis, and so on for the other axes. They're also showing you on this diagram the three unit vectors in the Cartesian coordinate system. A sub x is what I will be referring to as x hat. All right, it's a small vector that has unit length, and it points straight along the x direction. No matter where you are in space, the x unit vector points in the same direction. So if I'm, for instance, if I'm at the point 3, 4, 5, somewhere out in this quadrant here, in the first quadrant, or first octant, I should say, in 3 dimensions, the x hat vector still points in the same direction. It's not a function of position, and neither is the y hat or the z hat vector, and that's an important point that we'll come back to later. The Cartesian coordinate system also allows you to describe several constant coordinate surfaces. Okay, if you look at this plane here, this is a plane of constant x. If you'll notice, it's x equals something. It intersects this x-axis at some point, and y and z can be any number. Okay, so this particular coordinate, constant coordinate surface is parallel to the yz plane. If you look at the surface z equals some constant, it's parallel to the xy plane, and so on. For the surface y equals some constant, it's parallel to the xz plane. Again, it's useful to be able to visualize these constant coordinate surfaces in each of the three coordinate systems that we'll study. Well, circular cylindrical coordinates, or just simply cylindrical coordinates, are also extremely useful. Okay, we can represent the same point P now as three different numbers in cylindrical coordinates: rho, phi, and z. Okay, the rho coordinate tells you how far the point away is radially out from the z-axis. So this is the rho coordinate of this point P. The phi coordinate is this angle here that the projection of this little line down into the xy plane makes with the x-axis. Okay, so phi is measured from the x-axis to this line here. All right, so this coordinate rho, the rho coordinate, is a distance, and the second coordinate phi is an angle, and then we have one more distance, which is z. That is the distance simply from z equals 0 up to whatever height the point is at. Okay. Again, we can write the vector in a couple of different ways using this parentheses notation, which can be understood as this piece being the rho component of the vector, again the phi component, and the z component, a distance, an angle, and another distance. Or similarly, we can write it in the following way, where we put the rho component multiplying the rho hat vector, the phi component multiplying the phi hat vector, and the z component multiplying the z hat vector. Now, there is one very important difference between, well, several. One of the important differences between cylindrical coordinates and Cartesian coordinates is that in cylindrical coordinates, these little unit vectors here, if you notice, the rho hat vector a sub rho here and the phi hat vector a sub phi here, the direction in which those little vectors point depend on where you are in space. Okay, so you can imagine here that if this phi hat vector is at point P tangential to this circle of constant rho that wraps around like this, then if I move my point P up to here, then my phi hat vector is going to be pointing in a different direction than it is at this point. And similarly, if I'm over here, the phi hat vector will be pointing in a different direction. The important thing to understand about phi hat is that it's always tangential to a circle of constant rho. The rho hat vector, or a sub rho, points radially out from the line described from going from the origin through point P, essentially. It has unit length. Again, it's all of these unit vectors are called unit vectors because they have length 1, magnitude 1. But anyway, the rho hat vector just simply points right out here, normal to the tangent line to the circle of constant rho. And the z hat vector points straight up, and that is the exact same vector as in Cartesian coordinates. Now, the ranges of these variables, these coordinates, I should say, are also different. The rho distance doesn't go from minus infinity to plus infinity. It goes simply from 0 to infinity. Okay, it makes sense. It's hard to have a negative distance from 0, for instance. Similarly, the phi coordinate goes from 0 to 2 pi radians. In other words, from 0 here, that would be along the x-axis, wrapping all the way around to just on the other side of the x-axis, 2 pi radians. And the z coordinate is identical. It goes from minus infinity to infinity. We have some different constant coordinate surfaces here than we did in Cartesian coordinates, if you'll notice, this cylindrical surface here, like the surface of a pop can, is the rho equals some constant surface. So anywhere along this surface, the rho coordinate is the same. It's 3, it's 2, it's 1, it's something like that. This surface right here, this vertical surface, is the phi equals some constant. Say phi equals pi over 4, for instance, or something like that. Any point on this surface here corresponds to phi equals pi over 4. And then we also have a z equals constant surface, which is parallel to the xy plane, just like in Cartesian coordinates. Well, not surprisingly, it's useful to be able to go from Cartesian coordinates to cylindrical coordinates and from cylindrical coordinates to Cartesian coordinates. Okay, and this is just basic geometry here with a little bit of trig. But again, the point being that a person can understand a particular point in multiple coordinate systems. Okay, and it's the same point in three-dimensional space. But if a person wants to go from Cartesian coordinates to cylindrical coordinates, these are the relationships that you need right here. If a person wants to go from cylindrical coordinates to Cartesian coordinates, these are the relationships that you need. And they're completely equivalent. You can get from one to the other. But if you'll notice here, the rho distance is just the square root of x squared plus y squared. Okay. Phi is the arctangent of y over x, and z equals z, and so forth. Okay, so I suggest that in order to understand these relationships, just have a close look at this diagram, and they'll be pretty transparent. Now, getting back to what I said earlier about the rho and phi vectors being a function of position, one of the things that we can understand is that each of these unit vectors can be decomposed into a sum of the unit vectors in a different coordinate system. Okay, if you look at figure A here, what they're showing you here is this blue line here, this long blue line, represents the x hat vector. If you'll notice, it's pointing straight along the x direction. And what they're simply showing you is that this x vector can be resolved into a component along the rho hat vector here, and a component along the phi hat vector here that they're showing. Okay, so it's coordinate transformations really. They're simply showing you that this x hat vector can be decomposed into a projection along the phi hat and along the rho hat directions. The sum of those two vectors gets you x hat. And then the same over here for the y hat vector. This long blue line is the y hat vector, and they're simply saying again that you can resolve the y hat vector into a component along the phi hat vector and a component along the rho hat vector. Now I want to come over here to the Elmo for just a minute and put some additional relationships on the Elmo that are useful. Okay. In relating what we just did graphically to some algebra, you can express, for instance, the x hat vector in terms of the rho hat vector in this way: cosine of phi times rho hat minus sine of phi times phi hat. Okay, so all I'm simply saying here is that what you just saw graphically can be represented algebraically here. The x hat vector has two components, one along the rho hat vector, and the component along the rho hat vector is cosine of phi, and another component along the phi hat vector, which is minus sine of phi. Okay, we could say something similar about the y hat vector. Y hat is equal to sine phi hat plus cosine of phi hat, and the z hat vectors are identical in both coordinate systems. Okay, this would take you from cylindrical to Cartesian in that direction. Okay. The same can be said for the row, for the cylindrical unit vectors. We can go from Cartesian coordinates to cylindrical coordinates. Okay. And the relationships are the following. The rho hat vector may be written as cosine of phi x hat plus sine of phi y hat. The phi hat vector may be written minus sine of phi x hat plus cosine of phi times y hat. Just like that. And again, the z hat vectors are identical in both coordinate systems. That's just another way. This is just simply an algebraic way of understanding what we just saw. But what you really want to remember is the picture in your text. This figure right here. This really is the key picture that allows you to understand. Okay, I can decompose any unit vector in the Cartesian coordinates into a sum of unit vectors in cylindrical, and vice versa. Now, those little relationships that I just drew for you on the Elmo can also be written in matrix form. Okay, so if you again would like to go from Cartesian coordinates to cylindrical coordinates, so in other words, you're starting here with 3 components in Cartesian coordinates, and you'd like to get the corresponding components in cylindrical coordinates, you just compute this matrix vector product, just like this. This little matrix times this vector will convert from Cartesian to cylindrical, and similarly, though not identically, this matrix vector product converts you from cylindrical coordinates to Cartesian coordinates. You can go back and forth. Okay, what's the last big coordinate system that we're going to be studying? It's called spherical coordinates. Again, the same point P can be represented as 3 numbers, r, theta, and phi, small r, theta, and phi. In spherical coordinates, the first coordinate is a distance. It's the distance now from the origin to the point P. And then these other two coordinates are angles. We have the angle theta and the angle phi. The angle theta is the angle that this line here makes with the z-axis, and the phi coordinate is the angle that the projection of this vector into the xy plane makes with the x-axis. If you'll notice, the r coordinate, like the rho coordinate before it, goes from 0 to infinity. It may go from 0 to infinity. The phi coordinate only goes from 0 to pi, okay, or from 0 to 180 degrees. That's the theta coordinate, excuse me. The theta coordinate goes from 0 to pi radians, or from 0 to 180 degrees. And the theta coordinate goes from 0 to 2 pi radians, or from 0 to 360 degrees. Okay. In spherical coordinates, you can express a vector A in the following way, again using the 3 components, distance, angle, angle, just like this. Okay. Again, just like in cylindrical coordinates, these unit vectors change direction depending on where you are in space. It's a very important point to understand. So again, if we understand this r hat vector here, or little a sub r as they have it in your book, it points radially out. Okay, so if we start at the origin and draw a line straight through the point P, the r hat vector will have unit length and lie parallel to that line. Now the phi hat vector will be tangential to, if you're thinking about a ball with lines of longitude and lines of latitude on it, the phi hat vector is going to be tangential to a line of latitude that wraps around the ball. The theta hat vector, or a sub theta, is going to be tangential to a line of longitude wrapping around the ball. That's the way that, or the sphere, the globe, if you will, that's the way that I think about it. And again, now we have some different constant coordinate surfaces that can be useful depending on the problem that we're working on. This little spherical ball here, this is r equals some constant. Anywhere on the surface of that sphere, r is equal to the same number. Theta equals constant surfaces describe cones in spherical coordinates. Okay, so any point along this cone here, along the surface of this cone, is at the same value of theta. In other words, it's at the same angle from the z-axis. And then similarly, you can describe a plane in a vertical plane coming radially out from the z-axis as a phi equals constant surface in spherical coordinates. Again, it's useful to be able to go between spherical and Cartesian coordinates, and these little algebraic relationships will achieve that for you. So the r distance, the distance from the origin up to the point P, is just the sum of the squares of the Cartesian coordinates and so forth. I think the important thing is to look at this diagram and just see the geometrical relationships there. And if you need to do the calculations, once you understand the geometrical relationships, you can use these expressions pretty readily. Okay, well, just like before, we were talking about the relationship between the Cartesian unit vectors and the cylindrical unit vectors. You can see there's a relationship between the vectors in cylindrical coordinates, the unit vectors in cylindrical coordinates, and the unit vectors in spherical coordinates. If you look here at this diagram, here we've got the theta hat vector from spherical coordinates and the r hat vector from spherical coordinates, and we have the z hat vector from cylindrical coordinates and the rho hat vector from cylindrical coordinates. And all you really need to notice here is if you imagine a vector that's lying in the rho z plane here, it's going to be a two-dimensional vector. And if you remember from linear algebra, any two-dimensional vector can be spanned by two mutually orthogonal vectors. So if, for instance, we want to represent the r hat vector here in cylindrical coordinates, we're going to have a projection of the r hat vector along the z hat direction, and we're going to have a projection of this r hat vector along the the rho hat direction. The sum of those two projections will give you r hat. Similarly, if we want to instead represent z hat in spherical coordinates, again, if you just look, there's going to be a projection of z hat along the r hat direction and a projection of z hat along the theta hat direction. Okay, this is just to say that you can describe these vectors in multiple coordinate systems. Really, that's really the point of this. Again, there's some simple algebraic relationships that I won't go through in this case, but they can be written down in terms of a matrix vector product. So again, if you start in Cartesian coordinates and you want to go to spherical coordinates, you take this matrix vector product. If you begin in spherical coordinates and you want to end up in Cartesian coordinates, you take this matrix vector product. Okay, well let's look at a few problems here going back to the Elmo. Let's have a look at some examples that will hopefully be helpful to us.